Welcome to The Explainer. Today, we're setting the stage for an absolutely incredible real-world engineering case study. We're looking back at a massive project from a mature Middle Eastern oil field, where engineers faced an almost impossible mathematical challenge, and they turned to a radically new technology to solve it. It's a fascinating story about physics, massive amounts of data, and literally billion-dollar stakes.
So I want you to really think about this for a second. Would you trust an artificial intelligence with a billion-dollar decision? Now, in today's tech-obsessed world, maybe that sounds plausible, right? But imagine making that call back in 2005, in a highly traditional, physics-heavy industry that usually relies on decades of conventional math. Well, that is exactly the leap of faith the management of this giant asset decided to take.
Section 1. The high-stakes bottleneck.
Okay, let's dive right into this. What we're dealing with here is a highly complex, naturally fractured carbonate reservoir. We're talking about an enormous asset with over 160 horizontal production wells. It's like a giant underground puzzle. Now, to understand how this asset behaves, engineers built a traditional numerical simulation model, and it was massive, over 1 million grid blocks. To run just a single simulation on a state-of-the-art 12 CPU cluster at the time, that took 10 agonizing hours and cost about $3,000. They were hitting a massive brick wall. You simply cannot explore millions of different production scenarios when a single math problem takes a full workday to solve.
And the thing is, they desperately needed to run those scenarios because they were facing a massive risk. At the time, production was heavily restricted to a strict limit of 1,500 barrels of fluid per day per well. Management knew these wells could pump way more oil, but they were absolutely terrified of something called water cut. Basically, if you open the choke and pull too hard, you risk pulling in water from the periphery, bypassing the oil entirely and permanently ruining the well. They needed to know exactly which wells could be safely relaxed and which ones would literally drown.
Section 2. The AI proxy solution. So management made a really bold move. They shifted away from the old paradigm of computational brute force, where you're completely limited by physics-based equations grinding away for 10 hours, to a totally new data-driven paradigm. They commissioned a technology that could run a simulation not in hours, but in mere seconds. This was a total game changer. It allowed them to run hundreds of thousands, even millions of Monte Carlo simulations to exhaustively search for the absolute perfect production setup.
This incredibly fast new technology is called a surrogate reservoir model, or SRM. Now, it is absolutely crucial to understand that this isn't just some basic statistical curve-fitting tool. You can't just throw standard statistics at complex fluid dynamics and expect anything useful. The SRM is an advanced ensemble of machine learning technologies trained on the actual spatio-temporal data generated from those slow numerical simulators. Think of it as a really fast learner. It accurately mimics the complex physics of fluid flow, completely preserving the high resolution of the original model, but delivering the answers almost instantly.
Section 3. Predicting the 5 clusters.
So, the AI goes to work. It analyzed all 167 wells and categorized them based on their probability of success if their production rates were actually relaxed. It basically grouped them into 5 distinct clusters. The AI explicitly marked the wells in clusters 1, 2, and 3 as great, safe candidates for rate relaxation. On the flip side, it threw up a massive red flag for clusters 4 and 5, literally labeling them as terrible ideas that would just produce a ton of excess water.
And this comparison perfectly illustrates the stark contrast in what the AI was predicting. On the one hand, you have a top-ranked well from cluster 1. It shows this beautiful, steep slope of cumulative oil production with an incredibly low, flat water cut. It's exactly what you want. But then, on the other hand, a well from cluster 4 paints a totally different picture. The AI predicts that if you open the choke on this well, it's going to result in a disastrous 75% water cut.
Section 4. The real-world gamble.
Now, here's where it gets really interesting. Between January 2006 and February 2007, management actually authorized a real-world rate relaxation program for 20 specific wells. And the absolute genius part of this, they didn't just cherry-pick the AI's top recommendations. To truly validate if the AI actually worked, they purposefully selected wells geographically spread out across the entire field, intentionally including wells from all 5 clusters. They basically opened the chokes on the good picks and the bad picks to see if the AI's bold predictions would actually hold up in the real world.
What made this real-world test even more nerve-wracking were the extremely counterintuitive predictions the AI made. For instance, the SRM recommended some wells from clusters 1, 2, and 3 that were already suffering from high water cuts, some of them over 13%. The AI essentially said, "Trust me, open the choke, they're going to get better." Conversely, it warned against wells in clusters 4 and 5 that currently looked incredibly safe, with water cuts completely under control at under 3%. Any human intuition would tell you the exact opposite.
Section 5. The 5-year look back. Fast forward 5 years, and the definitive proof of the AI's counterintuitive logic is right here in the data. Looking at the maximum water cut before the test compared to after, focus on those seemingly bad wells in clusters 1, 2, and 3. The ones that started with high water cuts, they actually saw their water percentages drop significantly after relaxation. Because they ended up producing so much more oil relative to the water, the overall percentage plummeted. The AI hit the nail right on the head.
And what about the wells the AI warned them against? Well, it was a complete disaster, exactly as the model predicted. Those supposedly safe wells in clusters 4 and 5, which started with barely a trickle of water, failed catastrophically. Within just a few years of relaxing their rates, their water cuts absolutely exploded to 30%, and in some extreme cases, over 50%. The physical results proved beyond a shadow of a doubt that this AI had successfully identified the hidden, complex behaviors of the entire reservoir.
Now let's talk about the financial impact of trusting this data-driven model, because it was absolutely staggering. Over the course of the 5-year test, those 12 wells that the AI correctly identified as safe candidates generated an unbelievable $1.3 billion in incremental revenue. Let me repeat that, $1.3 billion. And they did this completely safely with negligible increases in water cut, meaning those wells remained perfectly healthy for future production.
Moving to the final financial tally, we really see how this cements the case for AI. The entire 20-well test generated over $1.9 billion in total. But pay close attention to those bad wells in clusters 4 and 5. Yes, they technically generated $533 million, but that revenue came at a severe and perhaps permanent cost. Those specific wells became dangerously waterlogged, with some actually in danger of needing to be completely shut in. It highlights perfectly why you need to know exactly which levers to pull and which ones to leave alone.
Section 6. A new data paradigm.
So the overarching point here is summarized beautifully by this famous quote from the legendary computer scientist Jim Gray. He called this exact shift the fourth paradigm for scientific exploration. We are moving away from purely theoretical and computational science, where we're constantly bottlenecked trying to force computers to solve massive physics equations. Instead, we use those simulations to generate vast amounts of data, and we let AI learn the entire system. We literally bring the computation to the data.
This explainer highlights a fascinating scenario where breaking out of the traditional modeling mindset unlocked well over $1 billion in value. And it really begs an exciting question. What other old-school, physics-bound industries are currently out there, artificially limiting their own potential, just waiting for their own massive data-driven revolution?